video is meant to take some problems that you guys want to see to review for our quiz on section 2.5 and 2.6 for next class. So when you want to write in standard form, remember there's a difference between standard form and factored form. This would be an example of factored form. And particularly what's special about this, besides being in factored form, of course, is that it also has real coefficients. Now, this problem didn't have any non-real terms, but I just want to point out that if it is in the direction that says factored form real coefficients, then there can't be any terms that have I in it. So if I wanted to write this in standard form means from highest to lowest, kind of highest degree, kind of all written out, multiplied out. And there's no real fancy way to kind of do this, to just kind of multiply out. Now, there are some problems that are definitely going to be easier to multiply out. So for example, I would multiply out x minus 1 quantity squared first. And I know it's a perfect square trinomial. It becomes x squared minus 2x plus 1. And then I know that x plus 2 quantity cubed, well, I know it's going to be x plus 2 multiplied by x plus 2 squared. If you remember your special case about the cubes, perfect cubes, you could do that. Most people don't remember it, so we'll just multiply it out just to practice anyway. Again, I know that this is x plus 2. I know that x plus 2 quantity squared is x squared plus 4x plus 4. So if I want to multiply this out, it's just purely multiplication. I know I'm going to multiply this term by this term by this term, and it really doesn't matter the order that you multiply them, so I'm just going to go ahead and multiply out this x plus 2 times this quantity and then multiply my final answer out. So it is going to be kind of messy. Obviously, it's going to be to the 5th degree because I look at my exponents and I know when I multiply it out, it's going to be the 5th degree in the end. So I'm just going to basically multiply out. So x times x squared is going to give me x cubed. X times 4x is going to give me 4x squared. And x times 4 is going to give me 4x. Now when I multiply, I know a lot of people just multiply and go straight across, but I tend to multiply by lining up, so I'm going to do that just to help you see that a little bit better. So I've multiplied everything by x, now I'm going to multiply everything by 2. So 2 times x squared will give me positive 2x squared, so I'll line that up underneath. 2 times 4x is going to give me 8x, so I line that up underneath. And then 2 times 4 is going to give me 8. And it's just nice to have it lined up because then when you multiply, you already see your like terms together, so it's very easy to just go ahead and combine them. Alright, so there is part of our problem. Now, I just need to multiply this down by our other trinomial here. And again, I'm just going to do the same thing. I'm just going to multiply it out. And again, I line them up upside down so I can kind of quickly see them. So I'm going to multiply by everything by x squared. So I've got x to the 5th plus 6x to the 4th plus 12x cubed plus 8x squared. Alright, so I've multiplied everything by x squared. Now I'm going to multiply everything by negative 2x. So negative 2x times x cubed is going to give me negative 2x to the 4th. Negative 2 times 6 is going to give me negative 12x cubed. Negative 2x times negative 12 is going to give me negative 24x, and negative 2 times 8, negative 16x. And again, I've multiplied everything by that, so I'm going to multiply everything by 1. That's pretty easy to do. It's just going to be x cubed plus 6x. Oops, I forgot my squared here. Plus 12x plus 8. So you can see the advantage of when you multiply lining them up, because then basically it's pretty easy to just combine your like terms. So it looks like this is going to be x to the 5th plus 4x to the 4th. Those 12s are going to cancel, so it's going to be plus x cubed. And let's see, we've got 14, so it's going to be negative 10x squared minus 6x plus 8. So this would be my polynomial in standard form. What if I want to find the 4th degree polynomial with real coefficients that has zeros of 1/3 with a multiplicity of 2 and negative 4 plus 3i? So we know if it's 4th degree, we know that there's going to be x to the 4th, and we know there's going to be 4 zeros. It tells us that one of the zeros is 1/3 with multiplicity 2, and I also have one of negative 4 plus 3i. And because I have one that's negative 4 plus 3i, I also know I have negative 4 minus 3i is also a 0. Now, here's what I notice a lot of people do on their classwork. When it says it's got a 0 of 1/3, a lot of people just said, well, it's just x minus 1/3, which true, it is correct. That is a factor for that. But multiplying out with fractions is really kind of messy, and so we want to know if there's another way that we can write this. Well, what else when you solve it will give us a solution of 1/3? Well, if you write 3x minus 1 as your factor, that also gives you a solution of 1/3. This is a lot easier to work with, so I'm going to work with that one. So I'm going to say 3x minus 1, and since it's multiplicity 2, I'm going to say squared. Now I need to work with this one. So I know that if I have a 0, so let's think about if we have a regular 0. If I said, for example, I had a 0 of 5, you tell me that the factor is going to be x minus 5. So if I tell you that the 0 is negative 4 plus 3i, you're going to tell me it's going to be x minus the quantity, negative 4 plus 3i. Now obviously we want to be careful because we want to make sure we distribute that if we're trying to get rid of that. And then of course if I have negative 4 minus 3i as a 0, that means the factor would be x minus negative 4 minus 3i. So I put the extra set of parentheses around here because when I go to multiply this out, it's going to be a lot easier to deal with if I go ahead and distribute the negative. If I distribute this negative to both my terms, it makes this a lot easier to look at. So this factor here will become x plus 4 minus 3i, and the second factor will become x plus 4 plus 3i. Now, when we write this out, once we've distributed the negative, we notice something special, hopefully. We notice that this term and this term are exactly the same, and this term and this term are exactly the same. The only difference between these two factors is one has a plus and one has a minus. This is just like our a minus b times a plus b special case, which when we know we multiply because it's a squared minus b squared. This is just a quick way to factor this out. So if I want to multiply it out, a squared would be x plus 4 quantity squared minus b squared, which is 3i squared. So all I need to do is basically say x plus 4 squared minus 3i quantity squared becomes minus 9i squared, but because I need to have real coefficients, I need to make sure that I substitute in for I squared with negative 1. This makes this x plus 4 squared plus 9. Now it says it wants to have fourth degree polynomial with real coefficients, so we have gotten rid of anything that's non-real, but it is going to be nice and easier to write it in factored form if this is simplified out. So not that it would be unacceptable to write this, but I'd want to be really careful if I do that because I need to have that extra set of parentheses here because technically this is one whole quantity. So what I would prefer to do instead is just go ahead and multiply that out. So this will become x squared plus 8x plus 16 plus 9. So when I multiply and then add those together, I get x squared plus 8x plus 25. And again, it doesn't say it has to be in standard form, and this is a factored form, and it does have all real coefficients, so it would be perfectly fine to leave your answer like this. Now let's look at one where you have to find all the zeros. So if I want to find all the zeros of this, first thing I know is I know that it's going to be degree 4. So we know we're going to have 4 zeros. Where do I start? This is not something that's easily factorable. We have a possibility of having real zeros and non-real zeros. So the first step that I would do is I would graph this in my calculator. So let's go ahead and do that. So I've gone ahead and put this into my calculator, and I've graphed our function, and it tells me that I look like I have 2 real zeros. And because I know that they cross through the axis, I know that if it was multiplicity, it would be an odd multiplicity. So we know that looking at this, there's going to be 2 real zeros and 2 non-real zeros. So now we just need to determine where those zeros are. I've fixed this window so you can see it a little bit easier for the scale, so each one of these represent 1. So we definitely have a value of 0 that's less than 1 and also one that's a little bit greater than -1 here. If I wanted to figure out exactly what values we had, I could try. I could just plug in, or I can plug in zeros. But you can also use your rational root theorem to think about possible factors. I know that since this value is somewhere between 0 and 1 and 0 and -1, and I know that when possible values I could have is 1 divided by something or 2 divided by something, I know that my value for my leading coefficient 9 had factors of 3, so my thoughts would be probably to try like 1/3 and 2/3. So if I trace and I want to type in, I can check and see. I get 1/3, that doesn't work. If I try 2/3, I believe that's going to be a 0. So we know that 2/3 is going to work. And if I try working backwards this way, let's try -1/3, and I find that that I think is also a 0. So the 2 real zeros that we have are going to be -1/3 and +2/3. So now we're going to take these and do synthetic division to find our remaining zeros. Alright, so we've done our synthetic division with the two real zeros that we found of 2/3 and -1/3. And notice that once I went ahead and did my synthetic division for 2/3, I went ahead and just used the leftover to find out the values with the 0 of 1/3. What I'm left with is 9x squared minus 36 plus 63. And we want to find those two remaining zeros. We know they're going to be non-real zeros because we taught that from our graph. I also know that if I want to solve this, I notice that all of these values can be divided by 9, so I would just go ahead and do that first because it just makes these values a lot easier to work with. So if I do that, then I'll get something that I can work with here. So once I've done that, I can see, is it factorable? Well, unfortunately, there's not two numbers that multiply to 7 that add to -4. So I know I'm going to have to do quadratic formula here. So I'm going to go ahead and plug it in. So I've got negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so I know I've got the square root of a negative number, which I know is going to give me I, and I know that the square root of 12 can be broken down into 2 square root of 3. So this is going to simplify into 4 plus or minus 2i square root of 3 because of the negative over 2. Both of these can be divided by 2, so I have basically 2 plus or minus I square root of 3. So my zeros are 2/3, -1/3, and 2 plus or minus I square root of 3. And this would be kind of the minimal work that you'd want to show on a quiz or test. Once you find your real zeros using your calculator, which is perfectly fine, you just need to show using synthetic division basically how you got what's remaining so that you can find the remaining two zeros. The other possibility, of course, is you could multiply those out and do long division, but I know how much you guys love long division, so this is probably the best choice for what you'd want to do. This last problem that I picked was especially important because it has something that's in degree 5, but also when you look at the graph, you'll notice something special about it. So we know we're supposed to have 5 zeros, so the first thing I want to do is take a look at the graph for this. Let's go ahead and take a look at the graph. So now that we've taken a look at the graph, we want to talk about particularly what kind of zeros we have. We can see that when we take a look at the graph, we definitely have one at 0, and that actually kind of makes sense because if I looked at all the terms in my function, they all had an x in them, so I could factor out an x. But we also have another real 0, it looks like at 1, and particularly that tells us something special. Because our degree is 5 and I see 2 real zeros, we know there can't be 3 non-real zeros because in this case we can't have an odd number of non-real zeros. We talked about that earlier. So what exactly happens at the 0 of 1? Well, we notice that instead of crossing through the axis, it goes back in the same direction it came from. This tells us it's got an even multiplicity. So if we have one of two situations that's going to happen here. Either they're all going to be real solutions, one at 0 and one with multiplicity of 4, or we're going to have 3 real zeros, 1 at 0, 2 at 1, and then 2 non-real. The only way we're going to be able to determine that is if we do synthetic division. So let's take our zeros that we do have of 0 and 1 with at least multiplicity 2 and go ahead and see what we get from that. So we know the real zeros we had. We know that 0 was a 0. And again, we notice that if we look at all of our terms, they all have an x in them. So the first thing I would actually do is just go ahead and factor out the x here. And that leaves me to show me that obviously I know I'm going to have a 0 of 0. Alright, so let's take what we have left over, and we know that one of our zeros was 1. So let's do our synthetic division. We know that we're going to need to do it twice because we know at minimal it's going to be an even multiplicity of 2. Okay, and let's go ahead and do our second one. Alright, so what's left over, it looks like, is x squared plus 9. Now, I can look at that and see that I know that it's not going to be multiplicity 4 because clearly 1's not going to be the solution here. So what is going to be the solution? Well, when I set this equal to 0, I can solve and say that x squared is going to equal -9, or when I take the square root, I'm going to have plus or minus 3i. So it looks like we have 5 zeros, so our zeros are 0, we have 1, which has multiplicity 2, and then we have plus or minus 3i. So those are my 5 zeros there.